Okay, so in this video, at the urging of a collaborator, I'm going to show how I get the strain rates in OpenSees from nodal velocities into the zero-length section element, which is something that's currently not implemented and that needs to be implemented. Okay, so what I have here is a simple script. I'm not going to draw anything. Be forewarned, this video may get a little boring if it's not already. But what we have is mass, a node that's fixed, and then two nodes that are free, single degrees of freedom, mass on each node, just some properties. All right, so then one element is connected to node one. It's an elastic material with E and eta. Eta is the viscosity, strain rate dependent. Okay, and then element two does the same thing, but goes through a section aggregator using material one, all right, but passing it through as just axial force deformation, as if it's a section, but both of these elements should give the same response if strain and strain rate are passed through accordingly. Here, just applying a step function to each node, nodes 1 and 2, do a little dynamic analysis. Okay, write an output file that spits out the nodal displacements. Okay, don't ask me why I did this in Tickle, but it's okay. Okay, so there's the results of running the OpenSees analysis, and if we look at the output, okay, first column is time. All right, second column is the zero-length element response. Third column is the zero-length section element response. Okay, they should give the same results, but they don't, which is expected. Okay, but you see that initially they start off at the same response, right? And then second column is damped, the third column is undamped. Okay, just go through. Right, you can plot these, but you can see that this one's damped out to something, right? Or sorry, column 2 is damped out to something around 0.665, right? And then column 3 just continues to go undamped. Okay, so how do we go into the source code and get the nodal velocities into the zero-length section element? Okay, again, this is going to be painful. I'm probably going to make a lot of mistakes, all right? But in doing so, you'll see some nuances of OpenSees. Okay, so I'm going to go into the zero-length section elements. Okay. Written by yours truly a while back, all right? But and since used to varying degrees of utility. Okay. All right, so let's see. Again, this is gonna get pretty boring. Don't say I didn't warn you. Okay, but, well, let's see. Let's first look at this regular zero-length element. Okay, so here's the regular zero-length element written by Greg Fenves, although Frank says he wrote it, but I don't know which one wrote it, but it's one of the more useful elements in OpenSees for sure, either way. Okay, so let's go to, what am I looking for? Sorry, not that. Search in the file here. Trial velocity. Yeah, here we go. Okay, so if you look at the regular zero-length element, right? In the state determination, well, that's in set domain. Okay, it's just figuring out the size of the node. But if we go to update, all right, for this element where the state determination happens, we're getting the nodal displacements. Node 1, node 2, you get the difference in displacement, whatever directions, right?
And then also we're getting the trial velocities, all right? Difference in velocities for whatever directions, translation, rotation, whatever. Okay, and then passing that off to strain and strain rate for the material. Okay, and then getting back the stress. Okay, but here's where we're getting the set trial velocity. Okay, from the notes. So if we go to update, since I just copied Greg and Frank's code, I probably did the same thing in update. No, I didn't. Okay, so let's go to get resisting force. What am I doing? Update. Let's just search for update. Here we go. Okay. So ZeroLengthSection update calls a private local function or private function for the class compute section deformations, right? So things are a little different. Yeah, okay, but basically here's the same business, right? So we're doing, you're getting displacements from the nodes, getting the difference, and then computing deformations, right? So all this code looks pretty much the same, right? Between the zero length on the left and the ZeroLengthSection on the right. Okay, so the crux, right, is that we need to get the velocities, right? So like every good object-oriented programmer or programmer in general, all right, we'll just get the nodal velocities. Copy paste. Sorry. Like every good programmer, you copy paste, you modify, right? Okay, so let's call this, it doesn't matter, V1, V2, call it whatever you want. Make that get trial velocity, get trial velocity. Okay, differential displacements, V2, V1, and like the excellent programmers, right? Or above average, right? You change the comments, right? Okay, after you copy and paste. Okay, that was a joke. Although you should. Okay, so what do we do here? Vector def. So this is a reference to a vector is equal to star v. Make the syntax nicer. So it's v must be a private variable for this class. We're probably about to step into a rabbit hole, but let's see what's happening. This is the header file for ZeroLengthSection. Yeah, here's v, section deformation vector. I only based it. So I'm just going to copy this, right? I'm going to add v dot section deformation rate vector, whatever. Okay. I'll initialize that in a second, but before we leave, right, before we leave this function, right, I think we just opened up a can of worms, but here we go. Def dot, call it whatever you want, okay? Def dot zero, so he's gonna zero it out, and then we're gonna loop over the materials and do the transformation on velocity, just like we do with displacements. Nothing magical here, right? So def dot diff v, right? And this tran ij is just the transformation matrix between the two nodes. Okay. So that will at least calculate the strain rates for the ZeroLengthSection element. I need a semicolon there. And let's see, I added this. I should go take care of that. All right, so that's a pointer. It needs to be first off initialized in the all the constructors. All right, so this is the regular constructor. Here's the default constructor, just initializing that pointer to null. And so we don't get a memory leak, we're gonna delete it in the destructor, it being the new vector pointer that we added, which is dynamically allocated. That's why we need to call the delete in the destructor. Okay. Somewhere in here we say v equals new. Yeah, all right. So I'm just gonna copy that, change everything, section, deformation rate, vector, dot, 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 dot. Great. Okay. Having tried, I probably should have been compiling all along, but let's see what happens. Well, okay, that's, oh, set transform v is also, I guess there's an extra check there. So I'm just gonna copy and paste and make this v dot. Sometimes you just find all the occurrences of what you're copying and just duplicate it, right? And then clean it up later. Okay, so that's done. Oh, it's reallocating. I see. Okay. All right. Yeah. So, oh, that's in, is that in receive self? Yeah, receive self. Okay. Okay. So set transformation, receive self. It looks like V is not sent. You don't need to send nodal things usually. But on the receive, we're just seeing if it's not, if the vectors are null. If they are, allocate based on whatever's being sent or received, right? And then go from there. Okay, so somewhere in here, get resisting force. Q equal, okay, so that's fine for strain rate, assuming strain and strain rate contribute to the same stress. What am I looking for? Set trial section deformation. Oh, update. Oh, yeah, I think yeah. Okay, so I'm pretty confident that I'm computing section, or yeah, I'm computing sections deformation rates, but there's nowhere to pass them to, or nothing to pass them off to within the section, right? Because here I would want to pass in V, right, which is section deformation vector. And I'd also want to pass in V dot, okay? But there's actually no functionality in materials section in the section force deformation interface. If you look at the header file over here on the left, right, see there's no, it's just set deformation, right? It takes a vector, right? A constant reference to a vector. There's no V and V dot or E and E dot or whatever notation you want to use. Okay, so, and this will open up just a whole new plethora of issues, right? But we need to add in another method, or probably a few more methods into section, right? That would take a strain rate, return a damping tangent, get damping stresses, if you want to separate them out from total stress resultants, depending on how you do material damping. So I may not succeed in my endeavor of getting that initial script that we looked at to work within this video, right? That's be another couple videos or something, right? But yeah, because if you look at uniaxial material dot H, right? You see things like this, right? Like set trial strain takes a strain and a strain rate. Okay. By default, the strain rate's 0. So if you don't pass 2 arguments, you only pass 1. All right, strain rate will just go 0 automatically. Right. Some other shenanigans for temperature. Let's not go there. And then some other set trial functions, but also incorporate strain rate. Okay. But there's nothing like that in section, right? It's all just static strain, right? Mechanical strain, no strain rate. So we actually need to add some functions to this interface, right? That will look like what's in uniaxial material. But instead of taking scalars, you're going to take vectors and return vectors, right? Okay. And then, also you see like in uniaxial material on the right, get damping tangent, right? There's no get damping tangent for the section that needs to be added, right? Yeah, I guess this interface assumes that you only get stress back from strain and strain rate, which is good, it's fine, right? But if you wanted to return damping stress separate from total stress, there's really nothing in this interface that would do that cleanly. Okay, so although I didn't get to my objective here of making this script work, which was probably just too ambitious, but or unrealistic. I didn't prepare for this, like every other lecture, right? So the idea, I think, is there, right? Like you gotta, or you have to add some methods to section force deformation, right? For deformation rates. But within ZeroLengthSection, we computed the section deformation rates, all right, from the nodal velocities. That was the easy part, right? We need to pass it down into the section, within this ZeroLengthSection update function, right? And then within when we do get resisting force, that's fine, all right? This should include strain rate effects. What about get tangent? No, get section. Oh, get tangent stuff. Oh, yeah, that's element. Yeah, sorry, I was thinking of the section interface. This is fine. All right, somewhat get damp. Yeah. Here, get damping tangent. All right, or get damp. All right, we'll need to extract out from the section and then transform, like we do up here with triple product, right? Transform the damping tangent from the section into element damping or damping matrix for the element. Okay, but I only managed to do the easy part, which was computing the section deformation rates from the nodes. Okay, but it's the first step. But then you got to dig down into section interface and go from there. Okay, so I hope this was helpful. If at any rate, or if anything, you got to kind of see a little bit about the inner workings of the OpenSees ZeroLengthSection, section force deformation, and to a small extent, the uniaxial material. Okay, so thank you.